Hey all, this is Mr. Jones, and this week we're going to be learning about chemical reactions, how to write them, read them, identify them, and most importantly, how to balance them. As usual with notes of this type, you want to write down any text that's in red and the examples when we balance equations. Those will be later on in the video. So first of all, let's talk about some definitions to help us understand chemical reactions. A chemical equation is defined as a well-defined example of a chemical change. We know a chemical change has occurred if new products are formed, as well as certain indicators like heat, gases forming, color changes, etc. For our example, we'll look at the formation of water. Water is formed through the chemical reaction between hydrogen gas and oxygen gas. So we write hydrogen and oxygen on the reactant side of the equation. Because they are what we are putting together. Water is written after the arrow because it's the product of the reaction or the new chemical reformed. So the left side of the equation is called the reactants, written on the left side of the arrow, and the right side is the product. The arrow in the middle stands for yields or makes and indicates that a reaction has occurred. Can we make equations shorter and easier to write? You may have noticed how much we had to write to show that reaction. Typically, we use chemical symbols and subscripts as a shorthand way of writing an equation. Using the same reaction as the previous slide, H2 plus O2 equals H2O, which represents hydrogen gas plus oxygen gas makes water. Both hydrogen and oxygen are diatomic molecules and are usually found in pairs. There is a problem though. How can two hydrogen and two oxygen make one H2O? That doesn't match up. The oxygens are different in number on the two sides of the arrow. We have two on the left and only one on the right. Law of conservation of mass. So the question on the previous slide about our oxygens not matching up has something to do with the law. The law of conservation of mass states that matter is neither created nor destroyed in a chemical reaction. So the reaction on the previous slide was not correctly written. We can't have oxygen disappear and all the elements on both sides of an equation must match or balance. To make an equation balanced, we use coefficients to determine the correct formula for the reaction that has the same number of elements on both sides. You may remember the word coefficient from math. If I put a 4 in front of x, that is a shorter way of writing 4 groups of x, like is shown on the bottom. All right, let's look at our original equation again, and this time I'll show you a picture to help you explain why this doesn't work properly. The yellow marbles represent hydrogen, and the red marbles are oxygen. The sticks and springs that connect them together are bonds. In our first example, you can see how the left side of the arrow has 2 hydrogen and 2 oxygen, represented by the 2 yellow marbles and the 2 red marbles. While the right side has a water molecule with 1 red and 2 yellow, H2O. We cannot change any of the reactants or products because that is how they are found in nature. In other words, you can't just pull one oxygen off the left side and call it good. They have to be balanced on both sides. So whatever goes in has to come out. We can only use coefficients or numbers in front of each formula to make it balanced. So we're going to go to the next slide to see what it looks like as a balanced equation. Balanced version of the water formation. So the balanced equation would look like this. I put lines in front of each of our molecules and we're going to write in coefficients to show how this equation can become balanced. You can see by the number of groups of the elements or molecules has changed from the previous slide. If we count the individual atoms of oxygen and hydrogen in the picture, we know that there is now the same number on both sides. 1, 2, 3, 4 hydrogens and 1, 2 oxygens. How do we show this on the equation? We knew before that our oxygen didn't match up. So we put a 2 in front of H2O I'm going to use my stylus real quick. We put a 2 in front of H2O. And that 2 tells us there are 2 groups of water on the right side. And you can see that by the 2 models that have 1 red and 2 hydrogens attached to it. So we have 2 groups of water on the right side of the arrow. But we also have 2 groups of hydrogen on the left side. So to show it, once again, using the stylus, I put a 2 in front of the H2, and now we have a balanced equation. You have two groups of hydrogen on the left for a total of 4, so think multiplication, 2 times 2 is 4. One group of O2, and no, we don't need to write the 1, and two groups of water on the right side. So we would say this equation as 2 groups of hydrogen plus 1 group of oxygen makes 2 groups of water. All right, we're going to be going through a couple examples, and the most important thing to kind of follow along with is just watch the process. Don't get frustrated if you don't get it right away, and as you see more and more examples, you'll get more comfortable with it. So we're going to go through a 3-step process when we're doing these. We're going to, first of all, we're going to check all the elements from left to right and see if they're balanced on both sides of the arrow. So think of the arrow as a tipping point where whatever's on the left has to match whatever's on the right of that arrow. If they are out of balance, we'll fix them by putting coefficients in front of the molecules. We cannot alter the original equation or the subscripts. So Zn and HCl and ZnCl2 and H2, we can't change those, only write numbers in front. And then last but not least, our coefficients have to be whole numbers. And please understand, this work can be some of the toughest content we've done all year. So be patient and keep trying as you are following along, and eventually you'll get it. So don't get frustrated when we're doing this. So going through the process, I'm going to read left to right. I'm going to do one element at a time. So our first element is zinc here on the left. So on the left, there's no coefficient. No subscript. In other words, no small number next to it. So that means I have 1 zinc on that side. On the other side of the arrow, which is our balancing point right there, there is also no subscript. So that means 1 zinc on the right side. Okay? So far, zinc is balanced on both sides. So I don't need to change it so far. Then, continuing left to right, we go to hydrogen. So hydrogen is the H. Once again, you'll notice there's no subscript, so that means there's only one of them next to that. We just don't write the ones. But on the other side, we have 2. And because of that, they're out of balance. This equation is not balanced. So I'm going to erase some of my scratch over here just to make sure we're clear on it. So knowing that it's out of balance, I've got to balance it. Zinc, we already said, was balanced, so I don't need to change it. But the hydrogen, I only have 1 on the left and 2 on the right. So you have to think of the coefficient as a way to multiply it. So I'm going to write a 2 in front of this hydrogen. And that means there are 2 times, or double, twice as many hydrogens on the left now. So that we have a total. Well, there was 1 before, so now there's 2 total. On the other side, we already had 2. So by putting that 2 in front, I had 2 hydrogens on the left and 2 hydrogens on the right. Now, that doesn't mean we're done though, because we have to keep going left to right. And so I'm going to switch colors here. We're going to move on to the chlorine. Chlorine right here has nothing written next to it to the right, no subscript, so that means 1. But when I wrote that 2 in front, it also affected the chlorine. So on my left side over here, I have 2 chlorine, 2 groups of 1. On the right side, I already had 2 groups of chlorine. So now, continuing left to right, and you want to do this as a check to make sure you got them all right. I'm going to go back and look at all the changes I made, and I'll use a different color here. I have, and if we're looking on the left side, my zinc, I have 1 zinc on the left, and on the right, I have 1 zinc. Okay, that 2 on the end by the Cl does not affect it, so I have 1 zinc on both sides. Hydrogen, when I wrote that 2 in red in the front of HCl, there was originally 1 H, and now there is 2 hydrogens. Think of it as 2 times 1 is 2. On the right, my hydrogen already had a 2 because it was H2, so that's balanced. And then finally with CL, I had 1, and when I put that 2 in front, it became 2 of them. And then on my right side, I also have 2. So by putting that 2 in front of H, or HCl, that made the whole equation balance. And some of these equations are that easy. Just putting one number in makes the whole thing balanced. I have 1 zinc on the left, 2 hydrogens and 2 Cls, and on the right I have 1 zinc, 2 Cl, 2 hydrogens. So it's balanced. All right, for this next one, we're going to show you the equation for the burning of phosphorus. And on the left side, we have phosphorus, which is P, plus O2 yields or makes P4O10. So going back to what we talked about before, we're going to think of the arrow as our balance point, and whatever I have on the left has to match what I have on the right. And this is a fairly easy example. If you're able to follow along with this one, you're usually going to be pretty good for most of the equations you'll see on the worksheet, probably at least half of them. So anyways, let's first start with phosphorus. On the left, ask yourself how many phosphorus there are, because there isn't anything written next to phosphorus. That means there is 1 phosphorus on the left. And when I look on the right, we look just to the next to it, and we see there's 4 phosphorus on the right. So pretty easy fix. If I have, and I hope I'm not confusing anything, and that's a 0. If I have 1 phosphorus on the left, then I need to multiply it by 4, as in 4 times 1 makes 4, which makes 4 phosphorus on the left and 4 phosphorus on the right. So by putting that 4 there, we have the same number on both sides. And now we go to oxygen. Oxygen has 2, because that's what's written to the right, on the left, and then oxygen has 10 on the right. So we have to ask ourselves, what do we have to multiply 2 by to get to 10? And of course the answer is 5, because 2 times 5 is 10. So I'm going to put a 5 in front of the O2. And then like always, and why I always say go left to right, just to make double sure, check that that 5 or that 4 didn't change anything else. And obviously on this one it didn't. I have 4 phosphorus on the right, 4 phosphorus on the left, 10 oxygen on the left, 5 times 2, and 10 oxygen on the right. So that is a balanced equation. And remember, I don't need to put the 1. I don't need to put a number in front of the lines. That's just places where you can have them. So that is a done equation. All right, the next one we have is formation of ammonia. So we have nitrogen gas plus hydrogen gas makes ammonia. So 2 gases make a liquid, kind of similar to what we did with water earlier. This one's going to be a bit more challenging. So if you can follow along with this one, you're doing very well. So I've got, once again, my left and right. So I'm going to got my little dividing line, and whatever's on the left needs to match whatever's on the right. Right off the bat with nitrogen, we see there are 2 nitrogen on the left, and on the other side, there's nothing written right there next to nitrogen, so that means there's 1 of them. Well, right off the bat then, the very first thing, nitrogen is not balanced. So I have to ask myself, what do I have to times 1 by to get 2? And of course the answer is 2. So that is the number that needs to go in for the coefficient. That makes 2 nitrogens on both sides. Then I go to hydrogen. Hydrogen on the left has 2 currently, because that's the number next to it. On the right, it has a 3. So, going back to something I said earlier, I can only use whole numbers. And so, to get from 2 to 3, I'd normally multiply by 1.5. Not going to be able to use that. So I need to think, what is a number? And this gets back to old school fractions, if you remember it. I want to find a number that is common, a multiple of it, kind of like the least common multiple or common denominator in fraction. I want to find a number that both 2 and 3 go into. And if you can think about it, 2 and 3 both go into 6. So I have to ask myself, What do I have to multiply on the left to make 6, and what do I have to multiply on the right? Well, that was already done for us. On the right side, we had that 2 there, and that actually made it 6. Because that 2, when it affected nitrogen, also affected hydrogen. So I had 6 of them back there originally. So to make the left side into a 6, I have to times it by 3. So I put a 3 in front of the hydrogen. If we go back and double check, we have 1 times 2 is 2 nitrogens on the right, 2 nitrogens on the left. 2 times 3 is 6 hydrogens on the right, and 3 times 2 is 6 hydrogens on the left. Next example. All right, formation of manganese chloride. Now, on this one, I've got, once again, my dividing line. And we'll start off with manganese, Mn, and I look on both sides. Neither one of them have a subscript, so that means I have 1 of both of them. So it's balanced so far. Then I get to chlorine. Chlorine on the left has 2. Chlorine on the right has 3. So similar to what we did on the last slide, I need to think about a number that both 2 and 3 go into, and that value is 6. So to make a 6 on the left, I would have to multiply it by 3. So that value is what I use for my coefficient. On the right side, I'd have to multiply by 2. So on the right side, my coefficient would be 2. So you might think, my equation's all done. I've got 6 chlorines on both sides and 1 manganese on both sides. But when I put that 2 in front of MnCl3, it also affects the manganese. Think like distributive property in math. It doesn't just affect the chlorine, it affects the manganese. So when I did that, I had 2 manganese as well. So to fix it, I have to go to the other side and also make 2 manganese. Now we have a balanced equation on both sides. So check that one. One more example. Now this time, this is your time to shine. This is the one I'd like you to try for yourself. And this has got a little bit of everything in it, so try your best. Remember, your balance point is in the middle between H2O and Fe2O3. This is how rust forms. So think of it, iron when it's left in water makes rust, and that's what happens. It also even gives off hydrogen gas when that happens. So I want you to try to balance this one. The answer's on the next slide, and if you're able to get it right, you're ready to start the handout. There'll be a handout called Identifying and Balancing Chemical Equations on Schoology for you. And if you can do this one, you can probably do about 3/4 of that one. Okay? So good luck on it. Email me if you have trouble, or log into the Zoom meetings on Thursday if you're having trouble with these, and try your best. Remember, don't get frustrated. It can be hard, but you'll get the hang of it. Good luck.